Long before the oceans we know today, Earth was home to massive superoceans stretching across continents and shaping life itself. What were these ancient seas like, and how did they influence our planet's history? In this video, we'll dive into Earth's distant past. If you enjoy this journey, please like, subscribe and share, and let us know in the comments, what do you think Earth would look like if those superoceans still existed? Thank you for joining us. Now let's begin. The planet moves as a single slow engine. Deep within the mantle, convection carries heat from the core upward, dividing the crust into large slabs known as plates. Over hundreds of millions of years, these plates drift across the surface, sometimes converging into one vast landmass, and at other times breaking apart into fragments. Each gathering of continents builds a new phase of the supercontinent cycle, and with each assembly comes a global ocean that surrounds it, a superocean. When continents cluster together, subduction zones rim the margins, drawing the seafloor downward and recycling old crust into the mantle. When they separate, new ridges open and create fresh oceanic crust. The alternation of spreading and subduction regulates the planet's surface over immense spans of time. Beneath this cycle lies heat flow that is uneven but persistent. Columns of rising hot rock called plumes weaken the lithosphere and create rifts, while cool descending slabs sink back toward the lower mantle. The thermal contrast drives motion that reshapes geography, climate and life. When a supercontinent forms, its interior becomes isolated from oceanic moisture and begins to dry. Around its edges, however, the superocean extends as an enormous basin, deep and continuous, wrapping around the world's single landmass. Its currents respond to planetary rotation and atmospheric winds, forming circulation patterns far broader than those of modern oceans. At the surface, the balance between continental crust and oceanic crust defines the hydrosphere's architecture. Oceanic crust is denser and thinner, sinking to form the depressions that hold water. Continental crust is lighter and thicker, rising to form highlands. When continents come together, they thicken through collision-lifting mountain belts that shed sediments into nearby seas. As the supercontinent grows, the surrounding ocean becomes proportionally larger, with ridges expanding outward to accommodate the moving plates. The superocean becomes both a sink for the planet's surface water and a mirror reflecting global change. Geologists trace this history by reading rocks that retain signatures of ancient positions. Magnetic minerals align with the planet's field when they form preserving directions that can later be measured. By comparing the magnetization of rocks from different continents, scientists reconstruct their former latitudes and orientations. When these reconstructions converge into a single mass surrounded by oceanic crust, the pattern reveals a supercontinent. The process is iterative and complex because oceanic crust is continually destroyed at subduction zones, leaving few direct remnants of ancient seafloors. Yet continental margins carry fragments, ophiolites, remnants of seafloor thrust onto land, and sediments deposited in former basins that provide partial maps of vanished oceans. Supercontinent cycles likely reach back at least 3 billion years. The planet's first stable continental nuclei, called cratons, appeared when the mantle cooled enough for thick crust to survive without rapid recycling. Over time, these cratons collided to form larger continental assemblies. Each episode marks a turning point in the circulation of heat and materials between the mantle crust and oceans. The merging of continents suppresses mid-ocean ridge activity, reducing volcanic gas release and altering atmospheric composition. Conversely, breakup renews ridge volcanism and accelerates weathering as new coastlines expose fresh rock. In this rhythm, the superocean alternates between contraction and expansion, its chemistry adjusting with each stage. The forces responsible for these cycles are physical, not predetermined. Mantle convection organizes itself into patterns that evolve slowly but continuously. Hotter upwellings beneath the lithosphere create zones of extension, while cooler downwellings generate compression elsewhere. The balance between these regions shifts as heat dissipates. When a continent passes over a superplume, it may rift apart. When it drifts toward a cluster of subduction zones, it may join with others. The result is a self-adjusting system that oscillates between union and dispersal. From space, if one could view the Earth during the age of a superocean, the planet would appear starkly divided between a single continental mass and a vast, uninterrupted blue plain. The ocean's surface would be marked by slow-moving gyres, thousands of kilometers across, driven by planetary rotation and atmospheric belts. Currents would carry heat from the equator toward polar regions, while deep circulation would move cold water back along the ocean floor. The interior of the continent would experience dry climates and large seasonal contrasts, while coastal margins would feel the constant influence of tides and storms crossing the superocean's breadth. Sediments along these margins accumulate in thick wedges, recording erosion from mountains and chemical exchange with seawater. Over time, they lithify into sandstone, shale, and limestone, forming archives of changing ocean chemistry. Within these layers lie isotopic ratios, tiny variations in oxygen, carbon, and strontium that reveal shifts in temperature, salinity, and biological activity. Each set of values becomes a clue to the state of the superocean at the moment of deposition. Climate during superocean phases depends on both geography and global carbon balance. When continents cluster near the equator, weathering draws down atmospheric carbon dioxide, potentially cooling the planet. When land concentrates near the poles, ice sheets can advance, raising albedo and further lowering temperature. Conversely, widespread volcanic outgassing during rifting releases carbon dioxide, warming the planet. The superocean moderates these effects through its immense capacity to store heat, but circulation changes can amplify extremes. Stagnant basins may develop low oxygen conditions, preserving organic matter that will later become fossil fuel deposits. As the mantle continues its slow motion, stress accumulates along the edges of the supercontinent. Rifts begin to open, guided by weak zones in the crust. Continental fragments drift apart, creating new seaways that grow into young oceans. The superocean, once continuous, becomes segmented, yet even in its fragmentation the record of its vast existence endures in magnetic alignments, metamorphous sediments, and mantle traces of subducted slabs. The study of superoceans is an attempt to reconstruct this grand pattern from incomplete evidence. Each rock formation, each mineral grain, is a remnant of processes that operate on timescales far beyond human experience. The cycles of assembly and dispersal shape not only the geography of Earth, but also the evolution of its biosphere, atmosphere, and climate. Understanding how these elements interact begins with recognizing the planet as a dynamic system, its surface continually reshaped by deep forces that rise, cool, and return to the core again. The earliest hints of superoceans appear as faint traces within the oldest rocks that have survived Earth's continual recycling. These traces do not preserve the oceans themselves, for oceanic crust rarely endures more than 200 million years before it is subducted and remade. Instead, scientists infer the existence of early global oceans from continental fragments and mineral records that hold chemical signals of seawater interaction. In ancient cratons, those stable continental cores bands of iron-rich sedimentary rocks, known as banded iron formations, testify to the presence of large standing bodies of water during the Archean and Proterozoic eons. These layers alternating between iron oxide and silica formed as dissolved iron in the oceans, combined with oxygen produced by primitive photosynthetic organisms. Their global distribution implies vast interconnected marine systems that extended across much of the planet. Paleomagnetic data provide another kind of clue. Tiny grains of magnetite within volcanic rocks lock in the direction of Earth's magnetic field as they cool. By measuring the orientation of these grains in ancient rocks, scientists reconstruct the latitudes at which those rocks formed. When samples from widely separated regions show parallel paths of movement through time, it suggests that they once belonged to the same continental block. When those blocks come together into a coherent cluster, the oceanic space surrounding them is inferred to have been continuous a superocean. Detrital zircon minerals, the oldest known fragments of the Earth's crust, extend the story further. Found in younger sediments, these microscopic crystals can be dated precisely, revealing the age of the continental crust from which they eroded. By comparing ages and isotopic signatures across continents, geologists map ancient sources and conclude when land masses were joined or isolated. The repetition of widespread zircon ages through deep time points to periodic clustering of continents, and by extension, periodic formation of immense oceans around them. In the early Proterozoic, nearly 2 billion years ago, evidence hints at a supercontinent known as Columbia, also called Nuna. Though its exact outline remains uncertain, reconstructions show continental masses arranged across equatorial latitudes, surrounded by a single broad ocean. Sedimentary belts of that age suggest extensive continental margins, where shallow seas accumulated carbonate platforms and muds, indicating long-term stability along broad coasts. Columbia's existence implies a preceding phase when its continents were separate, divided by oceanic crust that later closed through subduction. Thus, even without direct seafloor remnants, the cycle of ocean formation and consumption can be traced through the geometry of surviving continental sutures. The chemistry of ancient oceanic interaction is preserved within metamorphosed rocks that once lay near mid-ocean ridges. These rocks, rich in magnesium and iron, bear isotopic ratios of oxygen and strontium that differ from those formed in the mantle alone, revealing alteration by seawater circulation. When these rocks are uplifted and exposed in mountain belts, they become windows into vanished basins. Though small in scale compared with modern oceans, their global pattern demonstrates that seawater once circulated through extensive ridge systems connected across a unified hydrosphere. Glacial deposits from the same broad interval also inform superocean studies. When ice sheets extend over continents near the equator, they leave distinctive layers of tillite poorly sorted rock fragments embedded in fine sediment. Such deposits, dated to about 2,300,000,000 years ago, appear on several continents that were then joined, implying a global climatic connection, possibly mediated by a single vast ocean. The distribution of these deposits indicates that oceanic currents and atmospheric pathways were capable of transmitting cooling across much of the planet's surface. As the Proterozoic continued, continental blocks gradually reassembled into new configurations. The record of those changes lies in long mountain belts formed by collisions. Within those belts, high-pressure metamorphic minerals such as garnet and kyanite mark zones where the crust was thickened by continental convergence. Each belt traces a boundary that once divided separate ocean basins. The accumulation of these sutures over time demonstrates that earlier oceans closed, completely replaced by new oceans elsewhere. The repetitive closure of oceans and creation of others is the essence of the supercontinent cycle, showing that Earth's surface has been reorganized many times. By roughly 1 billion years ago, this process brought most continental fragments together, again forming the configuration known as Rodinia. Before this complete assembly, however, the exterior waters surrounding the growing landmass already displayed the characteristics of a superocean. The earliest evidence of that ocean comes from sediments and igneous rocks preserved along Rodinia's ancient margins. Geochemical data show that by this time global seawater chemistry had shifted, with rising oxygen and trace element patterns consistent with deep, well-connected circulation. These observations suggest the presence of a single planetary-scale ocean encircling the joined continents. Not all evidence aligns perfectly. Many of the rocks from this interval have been deformed, metamorphosed, or subducted, obscuring their original signals. Paleomagnetic records are sparse, and the orientation of ancient poles is debated. As a result, the exact geometry of early superoceans remains uncertain. Scientists must test multiple models against fragmentary data balancing tectonic reconstructions with chemical proxies and sedimentary clues. Yet even through this uncertainty, a consistent picture emerges. The Earth has repeatedly built continents into one body and encircled them with immense oceans that dominated surface conditions for hundreds of millions of years. In the absence of direct oceanic crust from those times, researchers rely on indirect indicators. Radiogenic isotopes in marine sediments capture shifts in continental weathering, pointing to the exposure of vast land masses drained by rivers entering one global sea. Sulfur isotopes record changes in redox balance between ocean and atmosphere. Trace fossils, though rare in such ancient rocks, reveal that microbial mats extended across tidal flats and shallow basins connected to a larger hydrosphere. Collectively, these records depict not a scattered archipelago world, but a continuous ocean system of planetary extent. The persistence of this pattern underscores how deeply interconnected Earth's interior and surface are. Mantle convection shapes continents, but oceans in turn influence the mantle by controlling sediment delivery to subduction zones and altering the temperature structure of descending slabs. This exchange of materials and energy sustains the long rhythm of assembly and dispersal that has characterized the planet since its crust first stabilized. In each cycle, oceans serve as both agents and archives, eroding mountains, moderating climate, and preserving the memory of vanished landscapes within mineral and isotopic codes. Thus, the earliest hints of superoceans lie scattered yet coherent across the oldest rocks. They describe a world already capable of vast hydrologic unity, its continents gathering and drifting above a restless mantle, its oceans opening and closing over spans of time beyond measure. From these faint signatures, the story of global seas begins a story that will continue through Rodinia's formation, through the rise of Mirovia, and onward to the more familiar oceans that followed. Rodinia forms slowly from a scattered arrangement of continental fragments. Over hundreds of millions of years, collisions between cratons build mountains that mark sutures where older oceans have closed. Sediments once deposited in shallow seas become folded and metamorphosed as continental crust thickens. The final configuration of Rodinia emerges around 1 billion years ago, when most major land masses have coalesced into a single large body centered near the equator. It is surrounded by a single global ocean, vast and deep, covering the majority of Earth's surface. The tectonic compression that joins the continents also builds highlands and volcanic arcs along their margins, shaping an irregular but unified landmass. To reconstruct Rodinia's assembly, geologists piece together ancient mountain belts that align across modern continents. The Grenville province in North America connects through time and structure to belts in Amazonia, West Africa and Baltica. showing where continental crust once welded together. Each belt contains deformed metamorphic rocks dated between 1 billion and 900 million years, the typical age of the collision events that closed earlier oceans. These regions now lie thousands of kilometers apart, but their shared mineral ages and structural patterns indicate that they were once neighbors. The matching of these features across modern oceans is the foundation for paleogeographic reconstruction. The assembly of Rodinia also affects the planet's thermal and chemical balance. As the continents merge, subduction zones become concentrated around their outer margins, reducing the total length of mid-ocean ridges. The lower ridge volume limits volcanic outgassing, which in turn may reduce atmospheric carbon dioxide levels. With fewer volcanic emissions and extensive land surfaces available for weathering carbon dioxide is drawn from the air and stored in carbonate rocks. The result could be a cooling trend that sets the stage for later global glaciations, although precise cause and effect relationships remain debated. At the surface, the newly formed supercontinent influences ocean circulation and climate. The interior regions of Rodinia far from the sea experience arid conditions. Seasonal temperature swings become extreme with hot days and cold nights across vast deserts. Along the margins, warm coastal currents flow from the surrounding ocean, bringing moisture that supports shallow seas and lagoons. The ocean itself likely exhibits slow wide gyres encircling the landmass, driven by planetary rotation and atmospheric circulation patterns, similar to those that operate today but on a far grander scale. Marine sediments deposited during this time record a distinct chemical fingerprint. The ratio of strontium isotopes in marine carbonates increases, reflecting enhanced weathering of continental crust exposed by mountain building. The oxygen isotopic composition of these same carbonates points to cooling surface waters. These geochemical trends align with the geological evidence of extensive continental uplift and erosion, linking tectonic processes directly to ocean chemistry. Rodinia's existence is not a static moment, but a phase in continuous change. Even as the final sutures close, the underlying mantle continues to move. Heat accumulates beneath the thick continental crust, weakening it over tens of millions of years. Volcanic activity appears along interior rifts, marking zones where the supercontinent begins to stretch and crack. The earliest signs of future breakup appear long before the supercontinent reaches its peak stability. In this way, Rodinia represents both culmination and prelude, a balance between construction and incipient disassembly. The supercontinent's large size also influences the biosphere. Cyanobacterial mats flourish in coastal shallows, generating oxygen that accumulates in the atmosphere. This oxygen reacts with iron and sulfur in the oceans, changing water chemistry and enabling more complex microbial life to expand. The combination of wide continental shelves and stable climates along equatorial latitudes promotes carbonate deposition, creating thick limestone sequences that persist as clues to ancient marine conditions. These sediments preserve microfossil spherical and filamentous forms whose shapes reveal the gradual diversification of early eukaryotic organisms. In the deeper ocean surrounding Rodinia, circulation patterns distribute nutrients and heat. The absence of polar ice allows thermohaline currents driven by differences in temperature and salinity to mix waters globally. Hydrothermal vents along mid-ocean ridges release minerals that feed microbial ecosystems. The chemical gradients around these vents resemble those found at similar settings, today suggesting that early deep-sea life already depended on sulfur and metal reactions for energy. Although the physical layout of the planet has changed repeatedly, the fundamental coupling between geology and biology endures. By comparing data from multiple continents, scientists estimate the approximate orientation of Rodinia. Paleomagnetic poles derived from basalt flows in North America and Australia suggest that the supercontinent straddled the equator, its long axis extending from high northern to high southern latitudes. This equatorial position influences global wind belts and storm tracks, intensifying tropical weather systems around the ocean margins. The single vast ocean precursor to later named basins such as Mirovia circulates freely around the landmass, redistributing heat and moisture. Despite broad agreement on Rodinia's timing, uncertainties remain about its exact configuration. Some reconstructions place parts of Siberia or East Antarctica on the periphery. Others position them closer to the center. The limitations stem from gaps in the record where erosion or metamorphism has erased key evidence. Nevertheless, all models show that by about 900 million years ago, Earth's continents were joined into one global assembly. This state marks the beginning of a superocean-dominated world, a period when ocean circulation and continental weathering operated at planetary scale. The tectonic pressures that created Rodinia eventually begin to wane. As subduction consumes old oceanic crust around the supercontinent's margins, the heat released by this process accumulates beneath the thick continental root. Mantle plumes rise from below, weakening the crust and promoting rifting. Within another 100 million years, fissures open that will ultimately fragment the landmass again. But for the interval centered near 1 billion years ago, Rodinia stands nearly complete, and the surrounding waters of its superocean define Earth's surface. The evidence of this immense configuration lies scattered across modern continents, each carrying pieces of a former whole. Folded belts record compression, rift basins mark later extension. Metamorphic minerals capture the temperatures and pressures of burial during collision, while igneous intrusions document the influx of molten rock as the crust adjusted to stress. Every sample adds another point to the global puzzle. Through them, the structure of Rodinia emerges not as speculation, but as a measured reconstruction grounded in the physical memory of stone. The ocean that surrounds Rodinia is known as Mirovia. Its name comes from the idea of a single global sea encircling one vast landmass, though the evidence for its full extent remains incomplete. What geologists can reconstruct points to a broad continuous body of water covering most of Earth's surface nearly 1 billion years ago. The oceanic crust beneath Mirovia, now long subducted into the mantle, left behind only indirect traces in continental margins, metamorphosed ophiolites, and the chemistry of ancient sediments. These clues together portray an immense interconnected hydrosphere that governed the planet's circulation and climate for hundreds of millions of years. To understand Mirovia, scientists examine the rocks that once bordered it. Along the edges of Rodinia's continental fragments, sequences of shallow marine sediments document the meeting point between land and sea. Thick layers of sandstone shale and carbonate mark ancient continental shelves, while deeper basins preserve volcanic ash and fine clays carried from the interior. In these deposits, chemical signatures such as strontium and neodymium isotopes reveal exchanges between the continents and the ocean. Their values shift over time as erosion from rising mountains alters the balance of materials entering the sea. By tracking these isotopic variations, researchers can infer the degree of continental weathering and oceanic mixing that once characterized Mirovia. The ocean's circulation patterns are harder to reconstruct. Unlike the modern world where continents divide currents into separate basins, Mirovia was nearly uninterrupted. Planetary rotation would have generated a series of wide gyres moving westward along the equator and eastward toward the poles. These currents redistributed heat, likely creating mild conditions across much of the planet. Without large polar landmasses, ice formation was limited, and global sea level remained high. The wide expanse of water also affected atmospheric circulation, moderating temperature contrast between equatorial and polar regions. As a result, weather systems may have been gentler but more uniform, with broad belts of wind and rainfall following steady latitudinal zones. Yet the calm surface concealed deep interactions between ocean and mantle. Beneath Mirovia, subduction zones ringed Rodinia's margins, consuming vast areas of oceanic crust. The descent of this crust carried water and sediments into the mantle, driving volcanism along continental arcs. Volcanic gases, chiefly carbon dioxide, sulfur dioxide, and water vapor, escaped back into the atmosphere, linking ocean chemistry with deep earth processes. These exchanges maintained a dynamic equilibrium, balancing weathering sedimentation and gas release over geologic time. The evidence of this balance survives in the isotopic record of carbonates and shales. Variations in carbon isotopes indicate alternating intervals of organic carbon burial and oxidation. Periods of enhanced burial suggest high productivity in surface waters, perhaps driven by nutrient upwelling along continental margins. Such productivity would have drawn down carbon dioxide from the atmosphere, contributing to global cooling episodes later in the Proterozoic. Conversely, intervals of reduced burial coincide with volcanic resurfacing events, when renewed outgassing restored greenhouse conditions. These alternating signals trace the rhythm of Mirovia's biogeochemical cycles. Fossil evidence from this time remains sparse but significant. Microscopic organisms left thin carbon films and mineralized shells in fine-grained sediments. Stromatolites, layered microbial structures formed in shallow waters, proliferated along coastlines and reefs. Their abundance in carbonate sequences demonstrates stable, warm and oxygenated conditions across wide continental shelves. Within deeper basins, organic-rich shales record the presence of life even where oxygen was scarce. Together, these rocks form a biological as well as geological record linking the superoceans chemistry to the evolution of early multicellular forms. Despite this growing body of evidence, the full geometry of Mirovia remains uncertain. Paleomagnetic data suggest that Rodinia's continental mass occupied low to mid-latitudes, but the exact orientation and rotation of the supercontinent are debated. Some models place Laurentia, the ancient core of North America, at the centre. Others situate Australia or Antarctica near the equator. Each configuration implies different oceanic pathways and climate regimes. Because oceanic crust from that time no longer exists, scientists rely on computer models of mantle, convection, and plate motion to test possibilities. These models simulate how heat flow and density variations could have moved plates, producing circulation patterns consistent with the observed sedimentary and isotopic data. Another challenge lies in the partial preservation of Rodinia's margins. Many have since been deformed or eroded during later tectonic events. Ophiolite fragments, sections of ancient seafloor thrust onto land, are among the few direct witnesses to the ocean that once surrounded the supercontinent. Their composition of basalt gabbro and serpentinized peridotite indicates formation at spreading ridges similar to those in modern oceans. Radiometric dating of these rocks often yields ages around 900 to 800 million years, aligning with the estimated lifespan of Mirovia. Though scattered and incomplete, these remnants confirm that active seafloor spreading and subduction were part of the superocean's history. As Rodinia matured, its vast size began to influence mantle dynamics. The weight of the thick continental crust insulated the underlying mantle, trapping heat and creating zones of buoyant upwelling beneath the supercontinent's interior. These thermal plumes gradually weakened the lithosphere, preparing the way for rifting. Evidence for such processes comes from large igneous provinces, massive outpourings of basalt that formed when the crust stretched and fractured. These provinces, found today in regions as distant as Siberia, Australia, and North America, share similar ages and geochemical signatures, implying a global-scale magmatic event related to the beginning of Mirovia's decline. During this transition, the chemistry of the ocean began to shift. Increased volcanic activity released new elements into seawater, including iron, phosphorus, and trace metals that enhanced biological productivity. Sediments record this change through higher organic carbon content and distinct mineral layers. In some basins, black shells rich in pyrite mark intervals of anoxia-oxygen depletion, suggesting that nutrient influx and restricted circulation periodically created stagnant conditions. These patterns reveal how tectonic and chemical processes intertwined as Rodinia approached its eventual breakup. The concept of Mirovia thus represents more than a single ocean. It encapsulates an entire planetary system operating as one. The circulation of water, heat, and materials across its vast expanse regulated Earth's climate and prepared the stage for the environmental shifts that followed. The data are incomplete, the maps uncertain, but the collective record magnetic isotopic sedimentary points consistently toward a time when a single continuous sea surrounded a single landmass. The study of this ancient ocean shows how the planet's surface interior and life have always been linked through cycles of creation, motion, and renewal that continue today beneath modern oceans. After hundreds of millions of years, Rodinia begins to fragment. Heat trapped beneath the thick continental crust builds pressure, and the lithosphere stretches. Rift valleys open across the supercontinent's surface, marking the beginning of new oceans. This stage in Earth's history transforms the once unified landmass into a chain of drifting continents surrounded by expanding seas. The ocean that forms first from Rodinia's interior fissures will become a Proto-Pacific realm, an immense basin that prefigures the later Panthalassa. Though the precise timing varies across regions, most reconstructions place the onset of rifting between 800 and 700 million years ago. The process begins deep within the mantle where rising plumes of hot rock weaken the crust. As the supercontinent expands from these centers, volcanic activity spreads across thousands of kilometers. Lava flows pour from fractures cooling into thick basalt layers that still outcrop in places like northern Canada, Siberia, and Western Australia. These ancient flood basalts preserve isotopic clues, showing that they originated from deep mantle sources, confirming that mantle upwellings played a central role in the breakup. Each volcanic province represents a pulse of activity that gradually pries the continental fragments apart. As the crust stretches the supercontinent's surface, buckles and sinks in places forming linear troughs, filled with sediments and volcanic material. These rift basins evolve into narrow seaways, where shallow waters circulate between newly separated blocks. Evaporites, deposits of salt and gypsum accumulate in the warm, restricted environments, while finer sediments settle farther offshore. The presence of these minerals in Neoproterozoic sequences confirms that early rift seas existed long before the full formation of new oceanic crust. Over time, these basins deepen as the crust thins and magma rises to create spreading ridges. The moment true oceanic crust begins to form marks the transition from rift to drift, when continents start moving away from each other. This fragmentation also reorganizes global circulation. Where Mirovia once enclosed a single supercontinent, multiple growing oceans now open between drifting landmasses. Water pathways change, influencing climate and sedimentation. With the creation of new seafloor volcanic gases, enter the atmosphere in large volumes, raising carbon dioxide levels and warming the planet. Yet geological evidence also points to dramatic cooling events during this same period, suggesting that volcanic weathering and continental rearrangement created complex feedbacks. Some intervals show evidence of widespread glaciation, including deposits left by ice sheets that reached near equatorial latitudes. These episodes, often called snowball Earth events, may have occurred as Rodinia's breakup redistributed continents and altered oceanic carbon storage. The birth of the Proto-Pacific Basin coincides with changes in seawater chemistry. Strontium isotope ratios shift, again showing an increase in continental weathering from the newly exposed margins. Sediments deposited along rifted edges contain iron formations and black shales, evidence for fluctuating oxygen levels in the water column. In some basins, thick glacial diamictites rest directly above marine carbonates, indicating that ice advanced over continental shelves before retreating suddenly. This pattern, repeated on several continents, records a period of climatic instability linked to tectonic reconfiguration. While the physical evidence for Mirovia disappears into subduction zones, its legacy continues in these new oceans. The Proto-Pacific Basin, though initially narrow, expands rapidly as rifting accelerates. Magnetic anomalies preserved in later crustal remnants reveal symmetrical patterns typical of seafloor spreading. Although direct remnants of Neoproterozoic oceanic crust are rare fragments preserved within younger mountain belts, provide hints of this process. These pieces, known as ophiolites, show the same layered structure, deep peridotite, gabbro basalt, and sediment cap that characterizes modern mid-ocean ridges. Their chemistry and age align with the expected timeline of Rodinia's breakup, linking them to the earliest stages of the Proto-Pacific's development. As continental fragments drift apart, new ecosystems adapt to shifting coastlines. Shallow marine environments expand enormously, creating wide continental shelves ideal for photosynthetic life. Stromatolite reefs reappear, and microfossil assemblages diversify. The rising oxygen content of the atmosphere and ocean, aided by biological activity, transforms global conditions. These processes collectively mark the transition from the stable Proterozoic world of Mirovia to the dynamic oxygen-rich planet of the late Neoproterozoic and early Paleozoic. The breakup also alters the mechanical behavior of the crust. Subduction zones develop along the new ocean margins, initiating a fresh cycle of plate recycling. Island arcs and volcanic chains grow above descending slabs, adding new material to continental edges. The arrangement of these arcs around the Proto-Pacific Basin resembles the modern configuration of the Pacific Ring of Fire, showing that similar processes operated even in ancient times. This stage introduces the tectonic framework that will persist through the Paleozoic expanding ocean basins bounded by convergent margins and complex island arcs. Paleomagnetic measurements confirm the widening separation between major continental blocks. Laurentia now centered near the equator drifts westward. Siberia and East Antarctica move toward higher latitudes. The resulting geography divides the once global superocean into multiple basins, each with unique circulation and sedimentary regimes. The transition from one global ocean to several regional oceans increases environmental diversity, promoting evolutionary change. It also resets the supercontinent cycle, beginning the long path toward the next configuration that will eventually unite the continents again as Pangaea. Even as the breakup proceeds, parts of Rodinia remain linked for tens of millions of years. Some sutures resist rifting, and others close again as microcontinents collide. These transient connections create small interior seas, transitional environments between continental and fully oceanic conditions. In them, sediments record both terrestrial and marine influences, evidence of fluctuating sea levels and shifting coastlines. Over time, erosion from rising mountains delivers nutrients to the oceans, fueling biological productivity that helps regulate atmospheric gases. Thus, even during disassembly, the feedback between geology and life continues to shape the planet. Eventually, the Proto-Pacific grows into the dominant global ocean. The continents that once formed Rodinia now ring its edges, just as later, continents will surround Panthalassa. Though the names and positions change, the pattern endures. Supercontinents assemble, superoceans form around them, and both evolve through cycles of creation and destruction, driven by mantle convection. The disintegration of Rodinia and birth of the Proto-Pacific mark one of the most significant reorganizations in Earth's tectonic and climatic history, setting in motion processes that will define the planet for the next 500 million years. When Rodinia's fragments drift into new configurations, one continent becomes dominant in the southern hemisphere. This vast composite landmass, later called Gondwana, begins assembling during the late Neoproterozoic and early Paleozoic eras. Its growth defines the next stage in the history of superoceans as surrounding basins evolve from the remnants of Mirovia into distinct new seas. Among them, the Paleotethys Ocean forms between the northern margins of Gondwana and smaller continental fragments moving away to the north. This ocean will play a central role in connecting future marine realms and in shaping global circulation for hundreds of millions of years. The assembly of Gondwana is not a single event, but a protracted sequence of collisions. Over tens of millions of years, continental blocks such as East and West Gondwana, India, Antarctica, Africa, South America, and Australia gradually merge. Their sutures remain visible today as ancient mountain belts, the East African origin, the Kunga Belt, and the Brasiliano Belt, each marking a former ocean that closed. These belts contain metamorphic rocks recording the high pressures and temperatures produced during collision. Radiometric dating shows that most of these events occurred between 600 and 500 million years ago, closing the oceans that had opened during Rodinia's breakup. As Gondwana consolidates, its outer margins define the boundaries of new ocean basins. To the north, the Prototethys and then the Paleotethys open, while to the west the Iapetus expands between Laurentia Baltica and Avalonia. Farther to the east, broad marine corridors connect these developing oceans to the larger exterior waters. The planet transitions from a world of small, scattered rift basins to one dominated by a few immense oceanic domains. These shifts in geography alter global climate and ocean chemistry, redistributing heat and nutrients across the planet. The Paleotethys Ocean occupies a unique position. It lies between the equatorial northern margins of Gondwana and a chain of drifting microcontinents that will later form parts of Asia and Europe. Along its southern edge, subduction zones consume old oceanic crust, producing volcanic arcs that line the Gondwanan margin. To the North seafloor, spreading creates new crust, extending the ocean's width over time. This dynamic balance between creation and destruction maintains an active circulation that exchanges water with neighboring basins. The ocean's existence can be traced through magnetic alignments, sedimentary facies, and the fossils of marine organisms that flourished along its shores. Marine sediments deposited during this era contain the first widespread remains of multicellular animals. Fossils of soft-bodied creatures appear in the late Ediacaran period, followed by shelled organisms in the Cambrian. The diversification of life in the oceans corresponds with changes in seawater chemistry. calcium, magnesium, and carbonate ions increase as continental weathering intensifies, supporting the formation of shells and skeletons. The expanding paleotethys thus becomes both a geological and biological frontier. Its shallow shelves host the earliest complex ecosystems, while its deeper basins preserve fine-grained sediments that capture chemical signatures of evolving seawater. Geochemical proxies from these sediments show that the paleotethys acted as a major carbon sink. The burial of organic carbon in anoxic muds drew down atmospheric carbon dioxide, influencing global temperature. At the same time, vigorous ocean circulation distributed oxygen to surface waters, allowing new ecological niches to form. The interplay between tectonic setting, ocean chemistry, and biological innovation illustrates how superocean dynamics control the course of evolution. Gondwana's stability provided the continental shelves. The paleotethys provided the stage on which early animal life expanded. Climate during this interval remains variable. Evidence from glacial deposits indicates that Gondwana experienced repeated ice ages, particularly near the South Pole. These glaciations lowered sea levels and exposed broad continental shelves. When ice retreated, transgressions flooded low-lying regions, depositing marine sediments far inland. The resulting stratigraphic cycles document the rise and fall of sea level over tens of millions of years. Isotopic measurements from these layers reveal fluctuations in global carbon balance, linking climatic shifts to the planet's evolving oceanic and atmospheric systems. The closure of earlier oceans during Gondwana's formation also contributes to long-term environmental change. Mountain belts erode, releasing minerals that react with atmospheric carbon dioxide and alter ocean alkalinity. This chemical weathering stabilizes the climate over geologic timescales. The widespread carbonate platforms that develop along the margins of the paleotethys record this stabilization. Thick sequences of limestone, dolostone, and shale accumulate, providing a continuous archive of marine conditions through the Cambrian and Ordovician periods. The presence of volcanic arcs along the southern margin of the paleotethys indicates that subduction remained active throughout this time. Volcanic ash layers interbedded with marine sediments supply datable horizons that help reconstruct the pace of tectonic activity. These layers also contribute nutrients such as iron and phosphorus to the ocean, stimulating biological productivity. The combination of tectonic motion, nutrient cycling, and biological diversification makes the paleotethys one of the most influential oceans in Earth's deep history. As Gondwana stabilizes, other continents begin their own migrations. Laurentia Baltica and Siberia drift northward, closing the Iapetus Ocean and forming new collisions that will later create the supercontinent Pangaea. The gradual convergence of these landmasses signals the end of the long interval dominated by Gondwana and the paleotethys. Yet for millions of years, this southern supercontinent remains the planet's central feature, its vast mass influencing currents, winds, and global temperature gradients. The ocean that borders it continues to regulate climate-absorbed carbon and sustain life, serving as a bridge between geological eras. The record of this transformation survives not only in the rocks of ancient mountain belts, but also in the microscopic isotopic traces preserved within marine minerals. These data reveal that as Gondwana grew, ocean circulation patterns became increasingly complex. The simple gyres of Mirovia gave way to tiered systems with distinct surface and deep water masses. This layering helped drive global oxygenation, a process that allowed complex life to spread beyond shallow seas. Thus, through its formation and stability, Gondwana and its companion ocean, the paleotethys set the foundation for the Earth's next major reorganization, the eventual convergence into Pangaea and the encircling Panthalassa. As Gondwana stabilizes, another ocean begins to define the next movement of the supercontinent cycle, the Iapetus. This ocean opens between Laurentia Baltica and the southern margin of Gondwana around 600 million years ago. It originates when rifts propagate through the crust, splitting off fragments from the great southern continent and creating a new spreading ridge. For tens of millions of years, the Iapetus widens, filling with young oceanic crust volcanic arcs and deep basins. Its existence, recorded today in the rocks of eastern North America, the British Isles and Scandinavia, demonstrates how Earth's surface alternates between union and dispersal in a rhythm governed by mantle convection. At its widest, the Iapetus Ocean may stretch several thousand kilometers. Its floor hosts mid-ocean ridges where basaltic lava erupts continuously, forming new crust that moves outward on either side. The process leaves symmetrical magnetic stripes within the seafloor, a pattern that modern geologists use to reconstruct spreading rates. These ridges rise as underwater mountains, while along their flanks hydrothermal vents release hot mineral-rich fluids that sustain ecosystems of microorganisms and primitive multicellular life. The water chemistry of the Iapetus records the combined influence of ridge volcanism, continental runoff and biological activity, an evolving mix that reflects both deep earth and surface processes. Along the continental margin, sediments accumulate in wide wedges. Rivers drain weathered mountains on nearby continents, delivering sand, silt, and organic matter into the ocean. Over time, these materials form thick sequences of sandstone, shale, and limestone. Their fossils capture early marine communities of trilobites, brachiopods, and mollusks that flourished during the Cambrian and Ordovician periods. The growth of these life forms signals a fully oxygenated ocean and the expansion of ecological complexity. The Iapetus thus becomes not just a geological feature, but a living ocean whose circulation patterns help distribute nutrients and oxygen throughout the biosphere. Its northern and southern shores evolve differently. Along Laurentia, passive margins develop broad, stable continental shelves with little volcanic activity. Warm, shallow waters foster carbonate platforms and coral-like reef systems that stretch for hundreds of kilometers. On the opposite side, near Gondwana's edge, subduction zones consume the oceanic crust, producing active volcanic arcs and deep trenches. These asymmetries reflect the constant interplay of plate forces creation at ridges balanced by destruction at trenches. As plates move, microcontinents and volcanic islands drift across the Iapetus, sometimes colliding with larger land masses to form transient mountain chains. Each collision closes a piece of the ocean, marking steps toward its eventual disappearance. Over time, these converging motions alter the geometry of the planet's surface. The Iapetus, once wide, begins to narrow as Laurentia Baltica and Avalonia drift toward one another. Subduction continues to pull the oceanic plates downward, drawing continents closer. In the sediments deposited along the closing margins, signs of compression appear: folded strata, metamorphism, and granitic intrusions associated with mountain building. These records are visible today in the Appalachian Mountains of North America and the Caledonides of Northern Europe, relics of the immense forces that closed the Iapetus and welded continents together into a larger configuration. The closure of the Iapetus triggers major climatic and biological changes. As continents collide, mountain ranges rise and alter atmospheric circulation. Newly elevated regions intercept moisture-laden winds, creating rain shadows and shifting precipitation patterns. Erosion from these mountains increases the flux of nutrients into rivers and seas, stimulating marine productivity. At the same time, volcanic activity along convergent margins releases gases that influence the balance of greenhouse and reflective aerosols in the atmosphere. The resulting combination of uplift weathering and volcanism may have contributed to episodes of glaciation during the late Ordovician, when ice sheets advanced across parts of Gondwana and sea levels fell globally. Fossil assemblages within former Iapetus sediments reveal how life responded to these environmental shifts. Marine diversity increases dramatically during the Ordovician radiation, when many new groups of animals appear. Later, as climate cools, extinction events reduce diversity, particularly among species adapted to warm, shallow seas. These biological turnovers parallel tectonic events, emphasizing the deep link between plate motions and evolutionary change. The formation and destruction of oceans not only rearrange geography, but also reset ecological systems. As the Iapetus closes completely by about 400 million years ago, Laurentia Baltica and Avalonia joined to form a single continental mass often referred to as Laurussia. This merger sets the stage for the later assembly of Pangaea. The sutures left behind by the closing ocean remain visible in the geological record as zones of metamorphism and faulting. Fragments of oceanic crust trapped between colliding continents known as ophiolites preserve direct evidence of the Iapetus seafloor. These rocks, rich in serpentinized peridotite and pillow basalts, confirm that spreading ridges and subduction zones once lay where mountain belts now stand. The life cycle of the Iapetus encapsulates the full rhythm of oceanic evolution birth at a rift growth by spreading maturity as a global corridor and closure through convergence. Its existence reshapes Earth's geography and leaves an imprint on global climate and biology that endures long after the ocean itself disappears. Each stage contributes to the slow choreography of the supercontinent cycle. When the Iapetus finally vanishes, its disappearance brings together the continents that will soon participate in forming Pangaea and the surrounding superocean Panthalassa. Even after its closure, remnants of the Iapetus persist in subtle ways. Geophysical imaging reveals that dense slabs of its former oceanic crust still lie deep within the mantle, having sunk hundreds of kilometers during subduction. These remnants influence mantle flow and may guide future patterns of plate motion. In this way, the memory of the Iapetus continues to shape the planet's interior, demonstrating that no ocean truly vanishes, it transforms and reappears in new cycles. Today, geologists trace this ancient ocean through matching fossils and rock structures, scattered across continents now separated by the Atlantic. The same trilobite species found in Scotland also appear in Newfoundland and Greenland, confirming that these regions once bordered a shared sea. In the deep roots of modern mountains, high-pressure metamorphic minerals preserve the final moments of collision. Each sample, when analysed, carries a fragment of the vanished ocean's story. The Iapetus, though gone for hundreds of millions of years, remains a quiet but enduring presence in the structure of the Earth. As the Iapetus Ocean vanishes, another body of water begins to take shape across the planet. This is the Rheic Ocean, a corridor of blue that opens between the newly merged Laurussia in the north and the still vast Gondwana to the south. It emerges around 470 million years ago during the late Ordovician, as fragments rift away from Gondwana's northern edge and drift toward Laurussia. In the long rhythm of tectonic cycles, the Rheic follows the same sequence as its predecessors' birth through rifting expansion, through seafloor spreading, and eventual closure through subduction and collision. Yet its position and timing make it an especially important link between earlier superoceans and the later configuration of Pangaea. The Rheic Ocean begins as narrow seaways within a complex mosaic of continental shelves and volcanic arcs, Shallow waters fill the gaps between microcontinents and the larger Gondwanan mass, creating new marine habitats. The rifting process triggers volcanic activity along the continental margins, producing thick flows of basalt that mark the earliest oceanic crust. As these rifts widen, the young ocean deepens and mid-ocean ridges form to accommodate spreading. The rake connects in time and space with other basins, including the Proterozoic and the still open Iapetus to the north, forming a network of corridors through which water, heat and life circulate. Sediments deposited along the margins of the Reich preserve a record of its expansion. Early deposits show coarse continental material eroded from nearby highlands, followed by fine-grained marine layers as the ocean deepens. These transitions mark the gradual shift from continental rift to mature oceanic basin. Within these sediments, fossils of planktonic graptolites and early pelagic organisms provide relative dating and reveal the development of open ocean ecosystems. The chemical composition of these rocks, particularly strontium, neodymium and carbon isotope ratios, shows that the Reich was in full communication with global circulation, exchanging water masses with neighbouring seas and helping to regulate Earth's climate. During the Silurian and Devonian periods, the Reich Ocean reaches its maximum width. Continental fragments such as Avalonia armorica and Iberia drift northward across its surface, carried by seafloor spreading away from Gondwana. The distance between these blocks and the southern supercontinent stretches to several thousand kilometers. Ocean currents, influenced by the arrangement of land masses and the prevailing wind belts, establish gyres that move heat between equatorial and temperate latitudes. These gyres transport nutrients that sustain rich marine life, evident in the thick accumulations of limestone and black shale that form along continental shelves. Coral reefs, stromatoporoids and early fish flourish in the warm tropical waters of the Reich margins. Meanwhile, subduction zones begin to develop along Laurushia's southern edge. The oceanic crust from the Reich descends beneath the continental margin, giving rise to volcanic arcs and deep trenches. Ash layers interbedded within marine sediments in present-day Europe and North America mark these episodes of arc volcanism. As subduction continues, the ocean begins to contract. The microcontinents that once drifted away from Gondwana now approach Laurussia, and collisions between them close portions of the ocean. The resulting deformation folds and metamorphoses sediments, forming mountain belts that will later compose the Variscan and Appalachian origins. The closure of the Reich Ocean unfolds gradually over tens of millions of years. During the Devonian island arcs and smaller continental fragments collide with Laurussia, adding crustal material to its southern margin. By the Carboniferous period, the leading edge of Gondwana itself moves northward, compressing the remaining oceanic space. Subduction accelerates as the last fragments of the Reich seafloor sink into the mantle. The collision of Gondwana and Laurussia marks the final disappearance of the ocean, producing one of the largest mountain-building events in Earth's history and setting the stage for the formation of Pangaea. The environmental consequences of these tectonic changes are extensive. Mountain uplift modifies atmospheric circulation and rainfall patterns. Newly formed highlands enhance chemical weathering, which draws down carbon dioxide and contributes to global cooling. The Carboniferous glaciations that spread across Gondwana are partly a result of this feedback. The burial of organic material in widespread coal swamps further reduces greenhouse gases, creating a cooler and more oxygen-rich atmosphere. In the seas, shifts in oceanic gateways alter circulation and nutrient supply, reshaping ecosystems. Fossil assemblages reveal turnovers in coral, brachiopod and trilobite communities as habitats migrate or vanish. The Reich Ocean also leaves its imprint in the deep structure of the continents. Seismic imaging shows that dense remnants of its subducted lithosphere remain embedded within the mantle beneath present-day Europe and North America. These slabs influence modern tectonics by altering mantle convection patterns. The suture zones where the ocean once lay now define major crustal boundaries, guiding later deformation and controlling the locations of mineral resources and basins. In this way, the memory of the ray persists not only in ancient rocks, but also in the architecture of the present crust. Chemical records preserved in Devonian and Carboniferous limestones capture fluctuations in the carbon cycle linked to the rake's lifespan. Periods of intense volcanism correspond with negative carbon isotope excursions, indicating increased volcanic outgassing. Intervals of high organic carbon burial align with positive excursions, marking times when vast wetlands and marine anoxic events sequestered carbon. These alternating signals reflect the constant exchange between tectonics, ocean chemistry, and climate. Through its formation, expansion, and closure, the ray ice ocean mediates the flow of elements essential for life. By the end of the Carboniferous, the continents have converged into a near-global assembly. The final suturing of Laurussia and Gondwana produces the Variscan Appalachian mountain chain, stretching thousands of kilometers across the equator. The last vestiges of the Reich Ocean are consumed, replaced by a continuous belt of highlands and volcanic arcs. The seafloor that once lay between them now resides deep within the mantle, its existence known only through the structures it left behind. Above, the atmosphere carries higher oxygen levels than at any time before, and vast forests blanket the continents. The world has entered a new equilibrium, one dominated by a single supercontinent surrounded by a single immense ocean. The Reich Ocean thus represents the final major step toward the creation of Pangaea and the encircling Panthalassa. Its opening, expansion, and closure illustrate the self-renewing mechanism of Earth's surface, where oceans are born and consumed in cycles lasting hundreds of millions of years. Through each phase, water, rock, and life respond in concert, reshaping the planet's face, while preserving the continuity of its underlying processes. The wreck may be gone, but its imprint remains in the mountain sediments and isotopic archives that still whisper the story of a vanished sea. By the close of the Carboniferous period, the Earth's continents have nearly completed their long journey toward union. The immense convergence of Gondwana from the south and Laurussia from the north brings forth a new supercontinent, Pangaea. Around it stretches the greatest ocean Earth has ever hosted, the Panthalassa. Its waters occupy more than 2/3 of the planet's surface, an expanse so broad that even the curvature of the planet cannot contain its scale in a single view. The closing of the Reich Ocean and the simultaneous fusion of continents complete one of the grandest tectonic reorganizations in planetary history, a transformation that will dominate the next 200 million years. The formation of Pangaea is gradual and complex. Multiple continental collisions unfold across different latitudes. Africa and South America collide with North America and Europe along long zones of deformation, forming the Variscan and Appalachian mountain belts. Further east, the northern edges of Gondwana merge with smaller terrains derived from Asia, generating the Uralian orogeny that unites Europe and Siberia. These convergences fuse nearly all major landmasses into one continuous continental shell that extends from pole to pole. The immense land area alters atmospheric circulation, ocean currents, and the global distribution of climate zones. The outer rim of this continental shell borders the superocean Panthalassa. Unlike earlier oceans, which were interrupted by island arcs and microcontinents, Panthalassa is almost uninterrupted. Its floor consists mostly of newly generated basaltic crust, spreading outward from a network of mid-ocean ridges that encircle the planet. The ridges act as heat vents for the mantle, their volcanic activity supplying vast quantities of gas to the atmosphere and minerals to the sea. The circulation of water over such an enormous basin operates on planetary scale. Surface currents are driven by the rotation of the Earth and the distribution of heat between the equator and the poles. These currents move slowly but continuously, creating gyres thousands of kilometers across. In the deep ocean, thermohaline circulation transfers cold, dense water toward the equator and returns warm water toward the poles, maintaining a slow but steady global exchange. Along Pangaea's coasts, the ocean's influence is felt differently depending on latitude. At the equator, warm waters lap against broad continental shelves covered by reefs and carbonate platforms. Farther north and south, cold upwelling currents bring nutrients from the deep supporting plankton blooms that feed rich marine ecosystems. These regions store organic matter that will over time become black shales and future energy sources. In polar zones, where the superocean meets glaciated coasts, icebergs carry debris far into open water before melting. The sediments they release fall through clear depths, creating varved layers that record annual cycles of climate and ocean dynamics. The interior of Pangaea, distant from the moderating effects of the sea, becomes an arid realm. The vast size of the continent limits the penetration of moist maritime air, producing deserts that stretch for thousands of kilometers. Wind-blown sandstones accumulate their cross-bedded layers, capturing the rhythm of ancient dunes. Yet along the coasts and river deltas life thrives. The carboniferous coal swamps give way to new ecosystems of conifers, ferns, and amphibians. Reptiles diversify, adapting to drier conditions. These shifts in life and landscape mirror the ongoing adjustments in ocean chemistry and atmospheric composition. The chemistry of Panthalassa evolves in tandem with the supercontinent's assembly. As subduction zones line nearly all its margins, the exchange between ocean and mantle becomes intense. Volcanic arcs encircle the basin, continuously recycling crustal material and injecting gases into the atmosphere. Carbon dioxide levels fluctuate with volcanic activity and rates of weathering on land. The balance between these forces controls long-term climate trends. Isotopic records from marine sediments show alternating intervals of warmth and cooling, suggesting that Panthalassa's vast size amplified global oscillations rather than smoothing them. Its immensity allowed regional differences in temperature and oxygenation that influenced biological patterns across the seafloor. The fossils preserved from Panthalassa's margins reveal a diverse and evolving marine world. In shallow tropical waters, coral reefs expand into massive structures dominated by new groups of organisms. Ammonoids, brachiopods, and early echinoderms populate the continental shelves, while in deeper zones radiolarians and planktonic algae flourish, leaving siliceous deposits that will later harden into chert. The distribution of these fossils across what are now distant continents confirms that they once shared a continuous oceanic realm. Even tiny microfossils serve as markers of global connection, demonstrating that currents linked every marine ecosystem within a single hydrosphere. The closure of older oceans and the rise of Panthalassa also reorganized the planet's carbon cycle. Organic-rich sediments deposited along the margins of the superocean act as long-term sinks for carbon, gradually locking atmospheric gases into the crust. This process, coupled with widespread glaciation during the Permian, lowers global temperatures and leads to the expansion of polar ice. Sea levels fall, exposing continental shelves and altering ocean circulation once again. Periodic anoxia develops in parts of Panthalassa's deep basins, where poor ventilation allows organic matter to accumulate. These dark layers in the sediment record mark the balance between life's productivity and the ocean's capacity to recycle its own waste. The dynamics of the superocean extend beneath the surface as well. Subduction zones surrounding Panthalassa pull its seafloor toward the mantle driving convection that keeps the system in motion. These descending slabs create arcs of volcanic islands and trenches that gird the supercontinent regions of constant geological renewal. The recycling of crust in this way helps regulate the thickness of the oceanic lithosphere and ensures that no portion of seafloor remains for more than a few 100 million years. The perpetual creation and destruction of crust sustain the tectonic engine that underlies the supercontinent cycle itself. Over time, the distribution of land and sea around Pangaea influences the planet's atmospheric patterns. With most land clustered into one hemisphere, monsoonal circulation strengthens, producing seasonal contrasts of heat and rainfall. Winds sweep across Panthalassa for thousands of kilometers, gathering moisture before striking the continental margins. These monsoons shape erosion rates and nutrient delivery to the sea, linking terrestrial and marine systems through hydrological feedback. The combination of arid interiors, humid coasts, and vast oceanic gyres defines the climate of the late Paleozoic world. Eventually, this configuration begins to strain under the same forces that built it. The immense mass of Pangaea insulates the mantle beneath, causing heat to accumulate and weakening the crust from below. Subtle rifts appear along continental interiors, precursors to the breakup that will follow in the Mesozoic. Even at its height, the supercontinent carries within it the seeds of its own disassembly. The surrounding Panthalassa will one day fragment into new oceans, the Pacific, Indian, and Atlantic, each a successor to the ancient waters that once circled an entire world. For now, however, in this deep time, Pangaea and Panthalassa stand as the dominant pattern of Earth's surface, a single continent encircled by a single sea, their equilibrium maintained by forces that never rest. Within the vast expanse of Panthalassa, circulation patterns evolve into complex systems that influence every aspect of Earth's environment. This ocean surrounding the immense landmass of Pangaea becomes the principal regulator of planetary temperature, atmospheric composition, and oceanic chemistry. Its size ensures that currents move slowly but steadily, transferring heat gases and nutrients around the globe. Though it seems endless and uniform, Panthalassa hosts regions of striking contrast zones of warmth and stagnation, of upwelling and turbulence, each shaping the biosphere above and the geologic record below. Scientists reconstruct these circulation patterns through the physical evidence preserved in sedimentary rocks and chemical proxies. Paleomagnetic alignments in seafloor fragments now incorporated into mountain belts reveal the orientation of spreading centers and subduction zones. Isotopic ratios in marine carbonates record the temperature and composition of seawater, reflecting the mixing of deep and surface currents. The data show that despite its vastness, Panthalassa was not static. Winds, tides, and differences in density created enormous gyres that moved counterclockwise in the southern hemisphere and clockwise in the northern. Equatorial currents carried warm water westward, while cold currents returned along the ocean floor, forming one of the earliest analogues of modern thermohaline circulation. At the surface, the trade winds generated wide belts of flow that converged in subtropical zones, producing areas of downwelling and nutrient scarcity. These regions supported fewer organisms and left behind carbonate-rich sediments. By contrast, along continental margins and upwelling zones near subduction trenches, nutrient-rich deep water rose to the surface, stimulating productivity. There, microscopic algae and plankton thrived, forming the base of the food web. When they died, their remains settled through the water column, forming thick layers of organic mud. Over time, these deposits recorded the interplay between biological life and physical circulation. Seasonal monsoons around the edges of Pangaea further modulated the superocean's currents. During summer, warm air over land drew moisture from Panthalassa, generating storms that brought rain to coastal plains. In winter, the reversal of winds produced dry offshore flow. This pattern, repeated over millions of years, left its signature in alternating layers of sandstone and shale that accumulated along continental margins. Each layer represents a balance between erosion on land and sediment delivery to the sea. Through such quiet records, the rhythm of superocean circulation becomes visible even after the water has vanished. The deep circulation of Panthalassa shaped global climate. When polar waters cooled and sank, they carried oxygen into the abyss, sustaining benthic ecosystems and preserving chemical balance. Periods when deep currents slowed correspond to intervals of oxygen depletion recorded in black shales. These anoxic events reveal how sensitive the superocean was to small shifts in temperature and salinity. A slight change in global heat distribution could disrupt the vertical mixing that kept the ocean habitable. The resulting oxygen-poor layers preserved organic matter that would eventually become hydrocarbons, an inheritance of stability and collapse written in stone. Currents also influenced the distribution of marine life. In equatorial regions, plankton flourished, feeding larger organisms such as ammonoids fish and early marine reptiles. Farther from nutrient sources, open waters were sparse in life, an immense desert of blue interrupted only by migrating species that followed invisible highways of temperature and chemistry. Along continental slopes, coral reefs anchored themselves in clear warm waters, their skeletal remains accumulating into carbonate platforms, visible today in limestones of Permian age. These biological structures not only recorded circulation, but also modified it, altering local flow and trapping sediments in shallow lagoons. The geochemical fingerprints of Panthalassa's circulation persist in the ratios of carbon and oxygen isotopes measured from fossil shells. Cycles of enrichment and depletion mirror shifts between glacial and interglacial climates, revealing how the ocean responded to long-term changes in atmospheric composition. During warm intervals, increased evaporation, concentrated salts, and intensified density gradients, strengthening thermohaline flow. During cooler intervals, expanded ice sheets reduced sea level, and freshened surface waters, slowing deep circulation. The interplay between these forces produced a self-adjusting system that maintained equilibrium over immense spans of time. Panthalassa's currents did more than regulate climate. They shaped the distribution of sediments that now compose much of the continental crust. Turbid currents sweeping along the seafloor transported fine material thousands of kilometers from their sources. These deep-sea fans, preserved today as folded greywackies and cherts within mountain belts, record the ancient pathways of submarine flow. Their mineral composition and fossil content vary with latitude, providing clues to the temperature and chemistry of the waters that carried them. Through their arrangement, scientists trace the outlines of vanished ridges, trenches, and gyres. The superocean also served as a vast reservoir for dissolved elements. Rivers from Pangaea delivered calcium, magnesium, and silica to its margins, while hydrothermal vents at mid-ocean ridges released iron, manganese, and sulfur. The balance between these inputs controlled ocean alkalinity and influenced atmospheric carbon dioxide. When volcanic activity increased, the supply of metal ions rose, enhancing nutrient availability and stimulating biological productivity. When weathering on land intensified, the drawdown of carbon dioxide cooled the climate. These slow feedbacks linked circulation to the deeper chemical cycles that govern planetary habitability. The immense scale of Panthalassa meant that climatic signals propagated slowly, A shift in polar temperature might take thousands of years to affect equatorial circulation. Yet the ocean's stability also made it vulnerable to long-term trends. Near the end of the Permian period, volcanic outpourings in what is now Siberia released vast quantities of carbon dioxide and sulfur gases into the atmosphere. The warming that followed disrupted ocean mixing, leading to stagnation and widespread oxygen loss. Black shale deposits from this interval show abrupt changes in carbon isotopes, marking one of the most severe environmental crises in Earth's history. The deep waters of Panthalassa became depleted in oxygen, and much of its marine life perished. This event illustrates the delicate equilibrium of superocean systems. Their immensity sustains stability, yet when that stability fails, the consequences spread planet-wide. The recovery from this crisis reshapes both oceanic and terrestrial life, setting the stage for the Mesozoic world. Through it all, the physical mechanisms of circulation, wind, heat, rotation, and density continue their ceaseless operation, rebuilding patterns of flow even as continents drift apart. The record left behind in marine sediments, isotope ratios, and fossil assemblages ensures that the movements of Panthalassa's waters, though long vanished, remain among the most deeply preserved rhythms of the planet's past. As Pangaea endures through the early Mesozoic, the configuration of land and sea begins to shift once more. The immense supercontinent, though stable in appearance, hides within its interior the thermal energy that will ultimately tear it apart. Beneath the crust mantle, convection continues its slow circulation, carrying heat toward regions of weakness that have persisted since the supercontinent's assembly. By around 200 million years ago, these internal forces begin to express themselves at the surface through rifting and volcanic activity. The same tectonic processes that once closed the Iapetus and Rheic oceans now start to open new basins that will lead to the disintegration of Pangaea and the reshaping of Panthalassa. The first signs of change appear along the future margins of the Atlantic and Indian Oceans. Stretching of the continental crust produces deep fractures that fill with basaltic lava and sediments washed in from nearby highlands. The Central Atlantic Magmatic Province, a vast field of volcanic rock forms during this period, marking one of the largest flood basalt events in Earth's history. The release of volcanic gases, carbon dioxide and sulfur compounds, alters the planet's atmosphere and may contribute to climatic instability. Layers of ash and tuff deposited in shallow marine environments record the interplay between rising magma and encroaching seawater. These deposits show that rifting did not occur all at once, but advanced in stages, dividing Pangaea first into northern and southern halves, known as Laurasia and Gondwana. While the supercontinent fractures, Panthalassa continues to dominate global circulation. Yet its currents evolve as new continental barriers redirect flow. The developing Tethyan Seaway, a broad equatorial passage between Laurasia and Gondwana, becomes an important exchange route connecting Panthalassa to smaller interior basins. Through this corridor, warm tropical water moves westward, moderating the climates of coastal regions and distributing nutrients that support expanding marine life. Fossil evidence from these margins shows a resurgence of coral reefs, ammonites, and early marine reptile species that thrive in the stable, well-oxygenated waters of the early Jurassic. As seafloor spreading accelerates, new mid-ocean ridges form within Panthalassa itself. These ridges reorganize currents, creating complex gyres and altering the balance of warm and cold water masses. The ocean's chemistry changes in response. Marine sediments record a shift in the isotopic ratios of oxygen and carbon, indicating warmer temperatures and higher atmospheric carbon dioxide concentrations. Evaporation increases, particularly along subtropical belts, leading to the formation of thick deposits of evaporate minerals such as halite and gypsum in restricted basins. These sequences mark the beginning of modern-style oceanic differentiation, where isolated seas and continental shelves evolve distinct chemical environments. Continental drift also reshapes habitats along the margins of Panthalassa. As the continents separate, long coastlines and shallow seas proliferate, creating new ecological niches. The expansion of continental shelves supports a burst of marine biodiversity known as the Mesozoic marine revolution. Predatory species such as ammonites, crustaceans, and early teleost fish diversify, exploiting the new food web sustained by nutrient upwelling from deeper waters. The fossil record shows an increase in shell thickness and defensive adaptations among prey organisms, evidence of intensified ecological interactions within the superoceans margins. Deep within Panthalassa, subduction continues relentlessly. The ocean floor created at mid-ocean ridges travels thousands of kilometers before descending back into the mantle. This conveyor-like system recycles water and sediments into the planet's interior, driving volcanism along the edges of Laurasia and Gondwana. The volcanic arcs generated by this process form Long Island chains, precursors to the future Pacific Ring of Fire. Their eruptions contribute metals and nutrients to the surrounding sea, fertilizing surface waters and sustaining plankton blooms that further influence atmospheric carbon levels. Through this constant interplay, Panthalassa remains the dynamic mediator between Earth's surface and its interior. The breakup of Pangaea progresses unevenly. In the north, Laurasia divides into the continents that will become North America and Eurasia. In the south, Gondwana begins to fragment into Africa, South America, Antarctica, India, and Australia. The spaces between these drifting plates evolve into the early Atlantic and Indian Oceans, while Panthalassa gradually transforms into the Pacific. Despite the birth of new basins, it continues to encircle most of the planet, its vastness absorbing the imprint of each tectonic change. Magnetic stripes preserved in oceanic crust dating from this time record the symmetry of spreading ridges, providing modern geologists with a map of the superocean's evolving geometry. Climate responds to this changing geography. As land masses drift apart, oceanic circulation becomes more efficient at transferring heat between hemispheres. Greenhouse conditions dominate much of the Jurassic and Cretaceous periods, producing warm polar regions and high global sea levels. Vast epicontinental seas flood continental interiors, their calm waters preserving fine-grained sediments rich in microfossils. These sediments, later uplifted into rocks, reveal fluctuations in salinity temperature and oxygenation tied to the evolving flow of Panthalassa and its successor basins. The isotopic signatures of these layers show oscillations between stable oxygenated intervals and transient episodes of stagnation, reflecting the sensitivity of circulation to small tectonic adjustments. The chemistry of the ocean atmosphere system also shifts with the growth of new ridges. Hydrothermal activity along spreading centers introduces metals and trace elements into seawater, altering its composition. Increased volcanic degassing raises carbon dioxide levels, but the expansion of continental shelves enhances carbon burial through biological productivity. This balance produces a relatively warm but stable climate ideal for the proliferation of marine reptiles, ammonites, and planktonic foraminifera. The fossil remains of these organisms now form the biostratigraphic framework through which scientists reconstruct the movement of continents and the pulse of the superocean system. Over time, the continuous spreading of new oceanic crust accelerates the rotation of plates and intensifies subduction around the Pacific margin. The result is a ring of volcanic arcs that mirror the curvature of the basin. This configuration focuses tectonic and thermal energy into a single dynamic system that persists into the present. The remains of Panthalassa's floor sink deeper into the mantle, forming slabs detected today through seismic tomography. These dense remnants mark the final stage of a superocean that once covered most of the planet. Even as it disappears beneath new oceans, its legacy endures in the global pattern of trenches, arcs, and ridges that define modern Earth. The breakup of Pangaea and the transformation of Panthalassa demonstrate the continuous renewal of the planet's surface. Oceans open and close in cycles that shape not only geography, but also life climate and the composition of air and water. The remnants of these processes, magnetic stripes, isotopic anomalies, folded mountain belts, and fossilized reefs, form a layered archive through which the deep rhythm of Earth's evolution can still be read. Each ridge and basin, each subducted slab, carries a portion of the memory of Panthalassa, the ocean that once encircled a world united by land. As the Mesozoic era progresses, the breakup of Pangaea continues to redraw the surface of the planet. What had once been a single vast landmass surrounded by the all-encompassing Panthalassa now fragments into several drifting continents, each accompanied by its own evolving oceanic basins. The process is uneven and slow, unfolding across tens of millions of years, but the consequences are global. Through this long transformation, the last direct vestiges of the great superocean begin to disappear beneath new crust. The geological and climatic balance of the Earth shifts toward the pattern recognizable today. Rifting intensifies along the lines of weakness that divide Laurasia in the north and Gondwana in the south. New spreading centers form within the fractures, generating young oceanic crust that pushes the continents apart. The early Atlantic begins as a narrow seaway between North America and Africa, while the Indian Ocean takes shape between Africa, Antarctica, and India. These nascent oceans are still shallow and partially enclosed, but they already display the thermal and chemical features of modern basins. Basaltic crust enriched in iron and magnesium emerges from mid-ocean ridges, while the first magnetic stripes record reversals of the planet's magnetic field. These linear anomalies preserved in the seafloor will one day become the principal evidence for plate tectonics, but in this ancient time they simply trace the invisible rhythm of spreading and renewal that defines the oceanic cycle. Meanwhile, the remaining expanse of Panthalassa, still covering most of the globe, begins to change character. As continents drift apart, the basin's symmetry is broken. Subduction zones around its margins consume old crust faster than new crust forms at its center. Deep trenches develop, ringed by volcanic arcs and island chains that rise from the sea. The Circum-Pacific system that emerges during this time is the early ancestor of the modern Pacific Ring of Fire. The descent of oceanic plates into the mantle drives volcanism, earthquake activity, and constant recycling of crustal material. In the process, vast volumes of water and sediment are transported from the surface into the deep earth, influencing both mantle chemistry and atmospheric composition. Sediments accumulating along these convergent margins capture the story of Panthalassa's decline. Thick wedges of grey-wax shale and chert form in deep marine troughs, later to be deformed and uplifted as accretionary prisms. Radiolarian microfossils within these rocks provide a continuous record of oceanic productivity. Their abundance and diversity change in response to shifts in nutrient supply and temperature, allowing scientists to trace the evolution of the superocean's circulation even as its physical boundaries vanish. The microfossil record reveals alternating intervals of high and low oxygenation, reflecting fluctuations in deep water renewal as tectonic rearrangements redirect the flow of currents. During the Jurassic and Cretaceous periods, climate remains warm and stable. The absence of large polar ice sheets and the high levels of atmospheric carbon dioxide result in elevated sea levels and widespread shallow seas along continental margins. These epicontinental waters host rich ecosystems of plankton ammonites and marine reptiles. Carbonate sediments accumulate into thick platforms that will later form limestone ranges across Europe, North Africa, and Asia. The geochemistry of these sediments shows that ocean circulation during this time is vigorous, with active exchange between the surface and the deep ocean maintaining global oxygenation. Yet beneath the apparent stability, slow changes in mantle, convection continue to reshape the seafloor and rearrange the geometry of continents and oceans. As India detaches from Gondwana and begins its northward journey toward Asia, a new ocean, the Neotethys, expands in its wake. This ocean, which replaces the earlier Paleotethys, becomes an important corridor connecting Panthalassa with the developing Atlantic and Indian basins. Warm equatorial currents move through it, carrying heat and biota across the planet. Marine sediments deposited along its margins preserve fossils of ammonites, belemnites, and early planktonic foraminifera that show the global connectivity of marine ecosystems. The presence of similar fossil species in distant regions such as Europe, the Middle East, and the Himalayas demonstrates how the Neotethys acted as a bridge within a still mostly unified oceanic system. In the deep interior of Panthalassa, the pattern of ridges and subduction zones grows increasingly complex. Multiple plates interact, colliding, diverging, and sliding past one another in a mosaic that defines the early Pacific plate network. Magnetic anomalies from this time preserved in fragments of ancient crust now embedded in island arcs suggest rapid reorganization of spreading centers. These changes alter oceanic circulation influencing global climate. Warmer equatorial waters and intensified upwelling drive high levels of productivity, as seen in the accumulation of organic-rich sediments. The burial of this carbon moderates greenhouse conditions, maintaining a balance that supports the flourishing ecosystems of the late Mesozoic. Yet this equilibrium is fragile. Toward the end of the Cretaceous, volcanic activity increases dramatically in several regions, notably in the formation of the Ontong Java Plateau, one of the largest volcanic provinces ever produced. The eruption of such immense volumes of lava releases greenhouse gases and alters ocean chemistry. Sediments from this time record a shift toward lower oxygen levels in the deep sea, culminating in brief but widespread anoxic events. These intervals, marked by dark shale layers enriched in organic matter and trace metals, signify disruptions in circulation that may have contributed to environmental stress leading up to the mass extinction at the close of the Cretaceous. The destruction of Panthalassa continues into the early Cenozoic. By this time, the Pacific Ocean has replaced it, bordered by newly formed continents and smaller marginal seas. Subduction consumes most of the original superoceanic crust, recycling it into the mantle. The last fragments persist as tectonic remnants embedded within modern oceanic plates. Despite its disappearance, the influence of Panthalassa endures in the patterns of mantle flow and crustal deformation that continue to shape the planet. The deep slabs descending beneath the circum-Pacific region represent the geological memory of the world's largest ocean, still guiding the convection currents that drive modern plate motion. The disappearance of Panthalassa marks the end of a full superocean cycle. The planet has transitioned from one global ocean surrounding one supercontinent to multiple interconnected basins and drifting continents. The balance of land and sea now resembles the present configuration, with diverse climates and ecosystems shaped by localized circulation rather than a single planetary system. Yet the processes that created and destroyed the ancient superoceans remain active beneath the surface, ensuring that the cycle will repeat again. Somewhere far in the future, continents will once more converge, and a new ocean will arise to encircle them, continuing the ceaseless rhythm that defines Earth's history. When the ancient waters of Panthalassa fade into the forming Pacific, the planet enters a new stage of oceanic and continental evolution. The early Cenozoic world inherits the fragments of this once global ocean, but the fundamental pattern of movement remains unchanged. Mantle convection continues to drive the slow drift of continents, spreading ridges, build new seafloor, and subduction zones consume it. The balance between creation and destruction persists, ensuring that no ocean is ever permanent. Though the modern world bears little resemblance to that of Pangaea, its structure still carries the imprint of the vanished superocean. As the Pacific replaces Panthalassa, it assumes its role as the primary oceanic reservoir of Earth. Its boundaries are framed by the arcs and trenches created by the subduction of older crust. These margins, inherited from the final stages of Panthalassa, form the foundation of the Circum-Pacific orogenic system. In the west, the margins of Asia and Oceania host chains of volcanic islands and deep-sea trenches, while in the east similar zones line the coasts of the Americas. This continuous ring of activity reflects the ongoing consumption of oceanic crust, a process that recycles material back into the mantle at a rate balanced by the generation of new crust along mid-ocean ridges. The chemistry of the new ocean reflects the cumulative legacy of its predecessors. Seawater composition evolves as volcanic, outgassing, weathering, and biological activity interact. Marine carbonates from early Cenozoic sediments record high levels of carbon dioxide and warm temperatures that supported abundant life. Over time, cooling trends emerge as continental uplift and chemical weathering draw carbon from the atmosphere. The isotopic ratios of oxygen and carbon in marine fossils show this gradual transition from greenhouse to icehouse conditions. In the polar regions, the first permanent ice sheets form, altering global sea level and initiating new circulation patterns. These changes demonstrate the continuing feedback between tectonics, ocean chemistry, and climate, a relationship established billions of years earlier in the age of the superoceans. As the continents rearrange, new gateways and barriers shape global circulation. The closure of the Tethys Seaway between Africa and Eurasia redirects equatorial currents linking the Atlantic and Indian Oceans. The opening of the Drake Passage between South America and Antarctica allows the development of a circumpolar current that isolates the Antarctic continent and reinforces cooling. These reorganizations mirror earlier transitions in the history of superoceans, when the creation or destruction of a corridor could transform the entire climate system. The Earth's hydrosphere remains sensitive to such shifts, responding to changes in geography, with alterations in wind belts, rainfall, and heat distribution. Sedimentary records from deep-sea cores reveal that circulation within the Pacific, the last remnant of Panthalassa, remains a central control on global temperature. Variations in the isotopic composition of benthic foraminifera trace the movement of deep water masses between basins. During warm intervals, stronger stratification isolates the ocean interior, reducing oxygenation and increasing the accumulation of organic carbon in sediments. During colder intervals, intensified mixing ventilates the deep ocean, restoring chemical balance. This dynamic equilibrium ensures the long-term stability of the biosphere, much as the ancient superoceans once did. Life within these evolving oceans adapts to new environmental conditions. The early Cenozoic sees the proliferation of modern planktonic groups, including diatoms and coccolithophores, which regulate the carbon cycle by sequestering carbon in their shells. Marine mammals evolved to exploit the abundant food sources created by upwelling zones, while coral reefs recover and expand in the tropics after surviving earlier extinctions. The distribution of these organisms reflects the interaction between oceanic currents and climate. Fossil assemblages show that species diversity correlates strongly with regions of nutrient exchange, a pattern consistent with models of circulation inherited from the superoceanic past. Beneath the seafloor, the process of subduction continues to mold the planet's surface. As slabs descend, they carry water and carbonates into the mantle, influencing melting and the generation of magmas. These processes release gases back into the atmosphere through volcanic arcs, maintaining the geochemical cycle that connects the deep Earth with the surface. Seismic imaging reveals remnants of ancient slabs from Panthalassa, still preserved deep within the mantle, their dense forms detectable by differences in seismic velocity. These ghostly traces show how each superocean leaves a physical memory within the planet, persisting long after its surface features have vanished. In the modern configuration, the Pacific occupies the role of both descendant and heir to Panthalassa. It is smaller than its ancestor, yet remains the dominant feature of Earth's hydrosphere. Its gyres, upwelling systems, and atmospheric interactions continue to regulate global weather and climate. The El Niño Southern Oscillation, a periodic fluctuation of temperature and pressure across the tropical Pacific, demonstrates how ocean-atmosphere coupling operates on human timescales, but arises from principles as old as the planet itself. The same balance of heat, motion, and chemistry that once governed Mirovia Panthalassa and the Paleotethys still governs the seas today. The study of these modern processes allows scientists to reconstruct the behavior of vanished oceans. Geophysical data from the seafloor isotopic analysis of marine sediments and modeling of mantle convection reveal patterns that echo those of the deep past. Through this integration of observation and theory, it becomes clear that the superocean cycle is not a singular episode but a recurring feature of Earth's evolution. Each phase assembly stability and fragmentation operates on a timescale measured in hundreds of millions of years. The Pacific will one day close and another ocean will arise to encircle a future supercontinent, continuing the sequence without end. In this perspective, the Cenozoic world becomes a bridge between the ancient and the future. It inherits the memory of the superoceans through the rocks that form its mountains, the isotopes that mark its sediments, and the currents that move through its basins. The processes unfolding today mirror those that have always shaped the planet, from the circulation of molten rock deep below to the gentle movement of surface waters driven by wind and heat. The Pacific, the Atlantic, the Indian, and all other oceans together form the dispersed descendants of the one ocean that once surrounded the world. Their collective motion carries forward the legacy of Panthalassa, a legacy written not in myth, but in mineral, in chemistry, and in the quiet persistence of water across time. The oceans of today, though far removed from the superoceans that once covered the Earth, continue to reflect the deep processes that govern the formation, transformation, and destruction of earlier seas. As the Earth's continents move ever so slowly across the surface, the oceanic system they surround shifts and adapts. Even as the Pacific Ocean, the largest and most profound remnant of the ancient superocean Panthalassa, continues to dominate the planet's hydrosphere, the entire oceanic framework remains in a perpetual state of flux. With every new cycle of subduction, rifting, and seafloor spreading, the oceans subtly shift their borders, reorganizing themselves and continuing the patterns that began in the time of the first superoceans. While the current oceanic system is largely shaped by the complex arrangement of continents, vast land masses that each carve their own influence into the surrounding waters, these boundaries are far from permanent. The steady drift of tectonic plates ensures that no ocean, however vast or seemingly eternal, is destined to remain unchanged. Subduction zones where one plate dives beneath another slowly consume the oceanic lithosphere. In their place, new crust is continually formed at mid-ocean ridges, perpetuating a cycle that echoes the creation and destruction of Panthalassa and its successors. Geological evidence of this ongoing process is all around us. Beneath the surface of the modern Pacific Ocean, remnants of the ancient superocean still survive as deep slabs that descend into the mantle, slowly being recycled into the Earth's interior. These slabs, known as subducted slabs, can be detected by their unique seismic signatures, which allow scientists to trace their journey from the surface to the mantle. In some cases, these slabs contain traces of ancient oceanic crust that once formed part of the oceanic floors of Panthalassa, now locked away deep beneath the earth. These lingering remnants are an enduring legacy of the vast superocean that once spanned most of the Earth's surface, their echoes reverberating through the mantle, as the Earth's internal dynamics continue their slow, inexorable cycle. Just as Panthalassa's remnants continue to influence modern tectonic processes, so too do the cycles of plate tectonics shape the modern oceanic system. Each shift in the movement of the Earth's plates alters the circulation of oceanic waters, influencing everything from climate patterns to the distribution of nutrients across the ocean. The opening and closing of oceanic gateways, narrow straits or seaways that connect different bodies of water, continue to play a critical role in global climate regulation. The opening of such gateways often brings warmer waters into cooler regions, while the closing of gateways has the opposite effect, isolating basins and leading to regional cooling. The Atlantic Ocean's current, for example, is greatly influenced by the constriction of the Isthmus of Panama, which allows the Gulf Stream to bring warm tropical waters northward into the North Atlantic. The oceans also remain a central driver of Earth's climate system. The circulation of warm and cold waters influences temperature and precipitation patterns across continents. Ocean currents act as a massive heat conveyor, redistributing solar energy from the tropics toward the poles and stabilizing global temperatures. As Panthalassa's immense scale once regulated the planet's climate, so do today's oceans, with their interconnected currents and vast surface areas, continue this age-old role. The persistence of ocean currents, which are now driven by wind temperature gradients, and the Earth's rotation, is a direct link to the ancient superocean systems that once spanned the planet. The interplay between ocean circulation and atmospheric processes is also evident in the modern world. The development of large-scale upwelling zones where deep cold waters are brought to the surface mirrors the nutrient cycling that occurred in ancient oceans like Panthalassa. These zones found in the Pacific Atlantic and Indian Oceans are hotspots of biological productivity, supporting some of the planet's most productive marine ecosystems. The nutrients carried up from the deep ocean sustain planktonic life, which in turn forms the base of the food web for fish, mammals, and seabirds. These upwelling zones, shaped by the same deep-sea processes that governed the ancient superoceans, remain the lifeblood of the oceanic biosphere. Biologically, the oceans continue to thrive, driven by processes that have been in place for millions of years. The cycle of upwelling and downwelling that regulates the flow of nutrients mirrors the ancient ocean circulation patterns that defined superoceans like Panthalassa. Modern marine ecosystems depend on these nutrient flows to maintain the productivity of the oceans. The vast kelp forests, coral reefs, and deep-sea ecosystems of today are all products of this long-standing relationship between ocean circulation, atmospheric composition, and biological life. The creatures of the sea, from the tiniest plankton to the largest whales, are all participants in an ancient ecological dance that has evolved over billions of years. Despite the many changes that have occurred since the days of Panthalassa, the fundamental processes that shape our oceans remain strikingly consistent. The formation of new oceanic crust at mid-ocean, ridges the subduction of old crust back into the mantle, the movement of oceanic water across vast distances, all these processes continue to drive the evolution of the oceans and their influence on global climate. However, the oceans are also undergoing changes that are directly tied to human activity. Climate change, driven by the burning of fossil fuels and the resulting increase in greenhouse gases, is altering the chemistry and physical properties of the oceans. Rising sea levels, ocean acidification, and the disruption of established current patterns are just some of the consequences of these changes. As the oceans continue to absorb heat and carbon from the atmosphere, they will undoubtedly play a major role in mitigating or amplifying the impacts of global warming. Despite these modern challenges, the oceans remain the planet's most important regulator. They continue to influence the Earth's climate-shape ecosystems and sustain life. The ancient superoceans, though long gone, have left behind a legacy that endures in the movement of water across the planet's surface and the slow, inevitable cycles of plate tectonics. Panthalassa, the great ocean that once surrounded the supercontinent Pangaea, may have disappeared, but its memory lives on in the processes that continue to shape our world. As the planet continues its slow march through time, the cycles of superoceans, continental drift, and oceanic circulation will continue. The remnants of Panthalassa, now deep within the Earth's mantle, will eventually give rise to a new superocean that will once again encircle a future supercontinent. And so the cycle will repeat in a slow, unbroken rhythm that has shaped the Earth for billions of years. In this eternal cycle, the oceans will continue to guide the course of life on Earth, as they have since the first superoceans formed, and will continue to do until the end of time. As the cycle of Earth's tectonic processes continues, the Earth's oceans, still largely shaped by the deep forces that govern the planet's surface, remain as dynamic and essential as ever. They are not merely passive bodies of water. They're active participants in the planet's ongoing geological and climatic transformations. Each shift in plate motion, each eruption at a mid-ocean ridge, and each subduction event not only reshapes the landmasses above, but also plays a vital role in driving the planet's weather-ocean circulation and biological evolution. These cycles, rooted in ancient processes that date back to the formation of the first superoceans, continue to influence every facet of life on Earth. Even as the current oceans appear stable, their role in regulating the planet's climate and maintaining life cannot be overstated. The global ocean conveyor belt, the vast network of surface and deep water currents that move water across the globe, remains one of the most important mechanisms driving the planet's climate. This system redistributes heat from the tropics to the poles, balancing temperatures and sustaining a global climate that allows life to thrive. These currents, which have existed in one form or another since the time of the superoceans, are a direct legacy of the ancient systems that once connected Panthalassa's waters to the landmasses of Pangaea. The changing of the oceans in the modern world is as much a product of human influence as it is of natural processes. Human activity, particularly the burning of fossil fuels and the release of carbon dioxide and other greenhouse gases into the atmosphere, has already altered the ocean's chemistry and physical state. Rising global temperatures lead to the melting of polar ice and the warming of surface waters, contributing to rising sea levels. The oceans, which have historically acted as a buffer against rapid climate change by absorbing much of the excess heat and carbon, are beginning to show signs of stress. This is particularly evident in phenomena like ocean acidification, which results from the absorption of excess carbon dioxide by the sea. While the impacts of human activity on the oceans are profound, the basic processes that have governed the oceans for billions of years remain. The movement of tectonic plates continues, reshaping the boundaries of the oceans and creating new seafloor as old crust is subducted. Oceanic basins once part of Panthalassa continue to shift, and new oceans will one day form as old ones close. The processes that created and destroyed Panthalassa, the opening of rifts, the formation of mid-ocean ridges and the closing of oceanic basins are still active today. Just as the oceans have shaped Earth's climate over millions of years, the climate of today is influenced by the oceans in complex and interdependent ways. Changes in ocean temperatures, currents, and salinity can have far-reaching effects on weather patterns, affecting rainfall, storm systems, and temperature distribution across the globe. The tropical Pacific, for example, remains a key player in shaping weather patterns, with phenomena such as El Niño and La Niña continuing to have a profound impact on global climate. These fluctuations, driven by the dynamics of ocean circulation, influence everything from agricultural production to the frequency of extreme weather events. Even the vastness of the modern oceans does not prevent them from being vulnerable to change. As the planet's primary heat and carbon reservoirs, the oceans are essential to the balance of Earth's climate system. The warming of ocean waters leads to the expansion of seawater, contributing to the rise in global sea levels. At the same time, the changing distribution of ocean temperatures influences atmospheric circulation patterns, affecting everything from storm tracks to monsoon cycles. These ongoing shifts remind us that while the oceans may be slow to respond to change, their impact is far-reaching and significant. The Earth's oceans in their current form are but one chapter in an ongoing story that stretches back to the time of Panthalassa. Over the course of geological time, the Earth's oceans have undergone countless transformations, each one shaping the planet in ways both subtle and profound. The superoceans of the past Mirovia Panthalassa and the various Paleotethys were the driving forces behind many of the planet's major geological events. The shifting of continents, the opening and closing of oceanic basins, and the dynamic exchanges of materials between the mantle crust and atmosphere all played a role in shaping life on Earth. Today we live in a world shaped by these processes, with oceans that continue to hold the key to understanding the deep history of our planet. The legacy of the superoceans is evident not only in the geological record but in the living world as well. The ocean's influence on life began with the earliest forms of life in the seas, which evolved over billions of years. From simple microbes to complex marine ecosystems, the oceans have supported life in ways that are still being uncovered by scientists today. The diversity of marine life from plankton to whales is a direct result of the ocean's ability to support complex ecosystems. This connection between Earth's oceans and life forms both ancient and modern is inseparable. The same processes that gave rise to early oceans and their accompanying ecosystems also played a role in shaping the course of evolution. The chemical composition of seawater, the availability of nutrients, and the movement of ocean currents have all influenced the way life on Earth has evolved. In this sense, the oceans are not merely passive witnesses to the evolution of life, they are active participants in the process. As the oceans continue to evolve both through natural processes and human influence, they remain at the heart of Earth's system. Their influence on climate life and geological processes is profound and ongoing. The lessons of the ancient superoceans, how they shaped the planet's surface atmosphere and life, can still be seen today. The superocean cycle, which began with the formation of early oceans, continues today, as the oceans of the world evolve and shift in response to both natural and human forces. The cycle of superoceans, from their creation to their eventual destruction, remains a fundamental part of the Earth's geological and climatic processes. Each new ocean that forms will follow a similar pattern to those that came before it, influencing the planet's surface, climate, and life. Just as Panthalassa once defined an era, so, too, will the oceans of the future continue to shape the world in ways we're only beginning to understand. The legacy of the superoceans is an ongoing story, one that will continue to unfold as the Earth's oceans evolve and adapt to the forces that drive them. The superocean cycle, though slow and measured, is a testament to the dynamic nature of the Earth's surface. The oceans in their vastness act as both a record and an agent of change. They hold the history of the planet's past, shaped by the same geological processes that continue to define the world today. In the future, as new superoceans form and old ones disappear, the cycle will continue shaping the Earth in ways that echo the ancient rhythms of the superoceans. Through it all, the oceans will remain the central force driving the planet's evolution as they always have.